Previously on So Much Code. Let's run this. Any moment now. Come on. Well, we know what the answer is, just output it. Well, it looks like it's not working. In my previous two videos, I never really mentioned what data Funciton deals with. I mean, I talked about integers and I showed you examples using 8-bit integers or sometimes bigger integers. So which one is it? Well, it turns out it's arbitrary size integers. So Funciton allows your integers to grow as much as you want, as long as they fit in your computer memory, obviously. But in return for that, that's all you get. Everything is integers. Now with that out of the way, let's take a look at what went wrong with our addition function that we were writing last time. So here's a nice little visualization of what 20 plus 50 looks like using the algorithm that we discussed. You can see at each step that we do the XOR and then the carry. And then after 3 iterations, the final number here is 0. And so this number here, which is 70, is the final answer. I also showed you that it works with negative numbers. So here as an example, we have negative 20 plus negative 50, giving you negative 70. Easy, right? And then I showed you an example with which it didn't work. That example was 120 minus 70. So what's going on here? Well, let's start looking from like this iteration onwards. You will see that there is the single 1 here, which of course will combine with this other one to create a carry. And then the next time the same happens with the next one, and then again and again and again. And you can see that if the size of your integer doesn't have a limit, then this will never finish, right? It will keep trying to eliminate more and more 1 bits, and the integers will just keep growing. It will never actually reach 0. So how do we fix that? Well, first of all, let me show that not all subtraction is broken. So you can have something like 50 minus 70 as shown here, giving you negative 20, which is the correct answer. So what cases are actually broken? Well, it turns out it works fine if both numbers are positive, as we've seen, and it works if the result is negative, as in this case, which is negative 20. But how do we determine if the result is going to be negative before calculating the result? Well, let's see if we can do some arithmetic manipulation. You remember that the number that consists entirely of 0 bits is of course 0, and the number that consists entirely of 1 bits is of course negative 1. And these are the bitwise not of each other. Now if I add 1 to the 0, and if I subtract 1 from this one, of course I get negative 2. You will see that those two numbers are also the bitwise negations of one another. And this will continue. So it seems that the bitwise negation of any number is basically the same as negative that number, but then minus 1. So we can write that as a formula. We can say that the negation of x is equal to negative x minus 1. And then I can rearrange that equation. I can put the minus 1 on the other side, and then flip the equation around. I will get negative x is equal to not x plus 1. Now we said that the addition function works fine if a plus b, in other words the result of the addition, is negative. Well, we can rearrange this equation by subtracting b from both sides. We get a is less than negative b. And now we can use the formula that we've just derived to replace that negative b with bitwise not of b plus 1. But now we have something less than something plus 1, and we're always dealing with integers, so that is actually the same as saying less than or equal to. So the addition function works if a is less than or equal to not b. Perfect! We know how to do bitwise not and how to do less than or equal to, so we can now easily check whether the addition function is going to work or not. But that raises the question, how do we fix it in the case where it's going to be broken? Well, logically that means that it must be broken if the opposite is the case, a is greater than the bitwise not of b. Well, let's play with this equation a little bit. First of all, let's apply this rule to change the not b back into negative b minus 1. And now I'm just going to negate both sides of the equation. And then we get negative a is less than b plus 1. And now let's use the other rule that we have to replace the negative a, and we get not a plus 1 is less than b plus 1. And now we have a plus 1 on both sides of the equation, and we can just remove those. Now, obviously, if not a is less than b, then not a is also less than or equal to b, because it's less than b. Okay, let me remove those extra steps that we did, and now let's take a close look at this. We see that the left side has a and not a, and the right side has b and not b. So that means that if we are in the broken case, we can actually just use bitwise not on both of the numbers, and we get a case that works. Now if we look at our visualization again, you can see that if I start by bitwise negating both of the inputs, so 120 becomes negative 121, negative 50 becomes 49, now the addition algorithm will work. It will eventually reach 0 here, but then the result it gets is negative 72, when we actually want positive 70. So what do we need to do? If we were to bitwise negate this, we would get 71, which is off by 1. So we actually need to add 1 to the number to get negative 71, and then the result of the bitwise negation will be 70, which is what we want. So that raises the question, how do we actually increment a number without using the addition function? Because we're trying to fix the addition function, right? So what does it actually mean to increment a number in binary? Well, let's take a random number like this one here, and we want to increment it. So we actually want 983, and it turns out that the binary for 983 is this. Now you'll notice that the only difference between these two numbers is in the last bit. So this number here had a 0 bit, we just add 1, it becomes a 1 bit. Okay, but what happens if the last digit is a 1 bit? Well, let's increment this once more, and we see that this time 4 bits have changed. The last 3 1s became 0s, and then a 0 became a 1, and nothing else changed. So what we really want to do is, for as long as there are 1 bits at the end of the number, we want to change them all to 0s, and then the first time we encounter a 0, we change that to a 1, and then we're done. Okay, there is only one complication with that, and that is that there exists one number, namely our familiar negative 1, which consists entirely of 1 bits, which means that we will never find a 0 bit, so we would never finish. So we're just going to treat negative 1 as a special case, because we already have an equals function that we can use to determine if our input is negative 1. So let's take this number as an example again. Here's how it's going to work. First, we check if it's negative 1, and if so, the answer is 0. If the last digit is a 0, well, we can check that by using bitwise AND with the number 1. Because if I bitwise AND with just the number 1, then this will mask out all of the bits except for the last one. So we will get either 0 or 1, depending on whether the last bit was 0 or 1. So if that gives us a 0, we know what to do. We just need to replace that bit with a 1 bit, and we can do that by doing a bitwise OR with 1. In the other case, where the number ends in 1, what exactly do we need to do? We need to do 2 things. 1, we need to replace that bit with a 0, and 2, we need to keep going. Now, keep going, we do that with recursion in Funciton, so let's do that here as well. So I'm going to shift right this number, which is the same as chopping off the last digit, and then keep checking if that is a 1, plop, plop. Eventually I'll reach the point where it's a 0, and then I'll change that to a 1, and then I will shift left the number again, and then we have our final result. 984 in this case. So let's implement that in Funciton. As usual, we start with a question mark because we need an if condition. We need to check if x, the input, I'm just going to call it x, is equal to negative 1. So we're going to call the equals function, but it doesn't matter where we put the negative 1 or the x, so I'm going to defer that decision until later. And if it is equal to negative 1, well then the answer is 0. So we put a 0 there. Else, we need another conditional. We need to check for the last bit. So we're going to put another question mark here. Now, take note of the fact that the first question mark that we did had its output pointing down, and so the condition was on the right. But now we want the result of that question mark to go in here. So this output is actually on the right, which means that the condition needs to go on top. Now, what is the condition? The condition, of course, is x and 1, the bitwise and. And in the case that x and 1 is true, in other words, not 0, well, then we want the complex case, which involves the recursive call. I'm going to call that the complex case. And in all other cases, we just want to bitwise OR with 1. So let's see how we can implement that. We know how bitwise OR looks. It's a bitwise NOT on both of the inputs and then an AND. So it would look like this. Now at this point you can see that we have a wire that needs to connect up with x, which of course is the input to the function. So I'm actually going to make the decision on the equal sign now. I'm going to have the x go down because now I can connect the two x's up and we end up with this. Alright, now let's take a look at the bitwise AND. Well, bitwise AND is the same as NAND followed by a bitwise NOT, so it would look like this. And I'm putting the x on the left here because I predict that the complex case is going to use x as well, which of course it is. So, what does the complex case actually consist of? The last thing that we need to do is shift left 1, right? After we're done with the recursive call, we need to shift left the number by 1. Well, fortunately, we already have a 1 box in the right place. That's very convenient, so we're just going to use that. And then before the shift left 1, we need to do the recursive call, so let's just put that box there. And then finally, we need to shift right x by 1, so we just put that there. But wait a second, we don't actually have a shift right function. But we do have a shift left function, and we know that it accepts negative numbers. So I'm actually going to write this as shift left -1. Okay, now we have these two wires labeled x. Well, we can just connect them up using a splitter. And then the other x, we can also join up with that. So this is the entirety of the function. So we just put the declaration box on the top, and ta-da, we have a function that increments a number by 1. Now, if you recall, this is the addition function that we wrote in the last video, which we found to be sometimes faulty. So we don't really want this to be the main addition function. We want the main addition function to be the one that applies the fix. So we're going to need to rename this function. I'm just going to put a p here to call it plus p. The p stands for private, but it doesn't matter, just as long as it's not called plus. And now we're going to write the actual plus function, which will just check for the special case. And if the special case doesn't apply, it can just call this function. And if it does apply, well, then we're going to do the bitwise NOT fix that we talked about, and then call this function. Here's what the real addition function looks like. I'm just going to paste it in here, and I'm quickly going to walk you through it. So at the output, of course, we have our question mark, which needs to check whether, well, it needs to check two things. It needs to check whether both of the inputs are positive, or a is less than or equal to not b. So first of all, here we're comparing both of the inputs against 0. Right, this one here is b, the second input. If you follow the lines, you can see that it goes in here. So this checks if b is non-negative. And the other one, a, goes around the top and then over here. And then this checks if a is greater or equal to 0. And then we want to AND that together. Now this is a NAND. You remember that AND was NAND followed by NOT. So imagine there is a little NOT there, and I'll explain in a second why it's missing. Now the other condition is that a is less than or equal to not b. So over here we have the b, and as you can see it goes down this line and it goes through this little box. So here we have the bitwise NOT of b, and it gets split here. So we're comparing that against a copy of a, which goes down this line here into this corner. So here, because the output of this less than sign is pointing up, we're actually checking if not b is less than a. What we wanted is not b greater or equal to a. So this is the opposite of what we want. So you could imagine another NOT here, and that would fix it. Now, why are both of those NOTs missing? Well, because we want to OR both of those results. We want to figure out if either the inputs are both non-negative or the special condition is true. And you remember that OR is like doing a bitwise NOT on both inputs and then NAND. So the NOTs just cancel out. So we end up with this very simple construct consisting of just two NANDs. So that's the condition for the question mark function. Now, in the case where that condition is true, we can literally just call the addition function that we've already written and that we've renamed to plus p. And in all other cases, well, we're going to use the bitwise not of both a and b. We're going to put those into the addition function that we've written, and then we're going to use the increment function that we just wrote to fix the discrepancy, and then do the bitwise not again. And ta-da, now we have a working addition function. So here's the same addition problem that we had last time, where we saw an infinite loop. And now if I just run this, you'll see that it correctly outputs 70, as you would expect. Well, this is exciting! We now have an addition function, we have an increment function. What else can we do with those? Well, here are some very simple functions that we can derive very straightforwardly from just those. Number one, unary minus, otherwise known as turn a positive number negative and a negative number positive. Remember this formula from earlier? Well, we can apply this directly now. Let's just very quickly draw a little declaration node for a hypothetical minus function, which I'm just going to call minus. And now let's straightforwardly just do what the formula says. The first thing is bitwise not, and the next one is plus 1. Well, we already have a function for that. It's called the increment function. And ta-da! We have a unary minus function. And we can easily combine the unary minus function with the addition function, which we've now fixed, to do subtraction. And then of course there's shift right, which we didn't have earlier, but now we can do it because we have a unary minus. We just need to make sure that the arguments are in the same order, hence the hook. Next one, what about absolute value? We know how to check if something is negative, and now we have a unary minus function to turn it positive. So absolute value should be a breeze. And you know what, I'm going to use this opportunity to show you that rotation really doesn't matter in Funciton. This function has its input go to the right and the output point to the right, and that means it behaves the same way as every other function that has one input and one output that just flow through the function in one direction. Another one, the decrement function. It's very easy, we just bitwise not, increment, and then bitwise not again. And now you understand how this part of the factorial function works. Yes, everything always comes back to the factorial function somehow. Well, actually that leaves us with only one box left in this factorial function that we haven't accounted for yet. Multiplication. You should definitely have a crack at this. Haven't we heard that before? But I really think you should. Now let me very quickly talk about algorithmic complexity. Take a quick look at this visualization of how 255 plus 1 works. Obviously I chose 255 because it consists of a bunch of 1 bits. This is basically the worst case scenario for a number that has only 8 bits. The entire algorithm needs to eliminate all of the 1 bits by doing a carry at every position, and so it needs 8 steps to finish. But notably, it doesn't need 255 steps. It only needs as many steps as there are bits in the number. And the number itself can be exponentially larger than the number of bits. What do I mean by that? Well, what I mean by that is if the number has 8 bits, then its size is round about 2 to the power of 8. If it has 16 bits, it's going to be 2 to the power of 16. So just in a sort of general order of magnitude. But you will notice that the number of steps in the algorithm always depends on the number of bits and not the size of the number. When computer scientists talk about algorithmic complexity, they say something like linear time or exponential time to describe how many steps an algorithm takes. And they mean that in relation to the number of bits in the input rather than the size of the number. So this is just a long-winded way of telling you that the addition function that we've already written is linear time. Because even in the worst case, it will only take as many steps as there are bits in the number. Now you could tackle multiplication the naive way, which is to just decrement one number, one at a time, and just add the other number on top of itself that many times. And that would give you multiplication. But if you think about it, the number of steps that you would need to do in that case is actually the size of that first number rather than the number of bits in it. In other words, that algorithm would be exponential time. Now, I'm telling you now that there is a linear time algorithm. In fact, remember when I used the factorial program to calculate 47 factorial? Well, take a look at this. Not only is it a very large number, but the factorial function actually calculates this reasonably quickly, 1.7 seconds. It would never be that quick if it were exponential time. It would take as long as the age of the universe. So my challenge to you is not just write a multiplication function, but write a linear time multiplication function. And I'll see you in the next video.